Okay, off we go. So let's see here. Yeah, don't forget about the attendance quiz. Attendance code is right here. You got a minute and a half, well, whatever. And by the way, about the exam, students have been asking me when the grading is going to be done, and we don't know exactly, but our target is to get it back to y'all by the end of this week. That's a goal, not a promise, right? So fingers crossed. But it should be by Friday. Okay. So picking up where we were last time. So here's another neat fact about gradients. And it's another neat fact about gradients that we can get to by thinking about directional derivatives. So we're going to consider this scenario where we are looking at a level set. Remember, you always have to keep the calculus of level sets in your mind sort of distinct from the calculus of graphs, distinct from the calculus of parametrized curves, etc. So here we're talking about level sets. Okay, so let's ask the question, if I'm at a point on that level set, such as that one in purple, and if I start moving with a velocity that is a tangent vector, how fast is f changing? Now this is just an academic question. Let's just kind of think it through. Okay, well, if I'm at this point and moving with that velocity, gosh, I can actually generate that scenario. I can make an actual scenario where I am in fact at this point and moving with that tangent vector velocity. The way I do it is just by making a curve that starts and remains and ends all on that curve. Now imagine this curve moving through this surface, namely moving on this level set. As I move along this curve, all I have to do is just aim for that point and be coming from such a direction that when I get to that point, the velocity is that tangent vector. And I know I can make that happen because this is tangent to the surface. Right? Does that seem like a plausible claim? And exactly what that curve is doesn't really matter. So, okay, again, we want to know how fast is f changing when I'm at this point and moving with that velocity. Said differently, how fast is f changing as I move along this curve? Well, this curve is on the level set. On the level set, f isn't changing. F is constant. So as I move along this blue curve, f is constant. And when something is constant, its rate of change is 0. That is kind of a neat observation. Now, what we're going to do with this is not yet clear, but if you're moving in the direction of a tangent vector to a level set, rate of change of the function is 0. Okay, now that noted, let's come down here, and I suppose I can go full screen, why not? And let's remind ourselves that directional derivatives, df ds is a directional derivative. Directional derivatives are computed with dot products, and so if I know that df ds is 0, that tells me that that dot product is 0. Now let me pause on that for a second. Right, so we argued that df ds is 0. When you're at a point and moving tangent to the surface, rate of change of f is 0. Now we have that a dot product is 0 because that's what df ds is. All right? Knee-jerk reaction, I hope, when you see that a dot product is 0, the first thing you should think is, okay, well, assuming one of those isn't the 0 vector, what we have then is that those two vectors are perpendicular, and just to get all of the possibilities in one word, they're orthogonal. Okay, now, let's keep that in mind, and let's remember which tangent vector was I looking at, and you'll notice I didn't specify. This works for any tangent vector. It works for all tangent vectors, right? So not only is the gradient perpendicular to that tangent vector, it's perpendicular to every possible tangent vector. What could the gradient be that's perpendicular to all of those tangent vectors, and I argue that there is only one possibility. That's going to be perpendicular to the surface itself. What do you think? Everybody buy it? Everybody see the reasoning there? It's a sort of a 3-step process to sort of, put the pieces together. But it's a really nice punchline, and it phrases very well. Let me color code. Keeping in mind that the surface we were looking at in the first place was a level set. Gradients are always orthogonal to level sets. Really cool fact, powerful fact. This is one of the big facts of what I like to call the calculus of level sets, right? Y'all have heard me say this a million times. We do not conflate the calculus of graphs with the calculus of parametric curves with the calculus of level sets. This is kind of one of the big facts of calculus of level sets. Level sets are always perpendicular to gradients. Okay. Neat fact. Now, this is a for y'all to read kind of thing. I'm going to go through and hit the highlights as I usually do, but there's a lot of little detail devils to think through. The question that comes to us, let's see here. How do we find the formula for the tangent plane? And of course, we already know the answer. The answer is tangent plane is the graph of the linear approximation. We already know how to do linear approximations. So why are we entertaining a question we already know the answer to? It turns out there's a really cool trick that we can play here. I think this is really nice. Arguably a better way to derive the equation of the tangent plane. And keep in mind, we started by looking at a graph. So this surface, right? Certainly if you're doing linear approximations and talking about the graph of the linear approximation, stuff like that, we're interested in graphs. It's a graph specifically of this function f. So we're looking at a graph. That's what a graph is. This function f. But keep in mind, anytime you have a graph, let me do it like this. Anytime you have a graph, you can reinterpret that as a level set. And I'm just going to pull that little algebraic fast one that we talked about back in, whenever that was, 2.3. Let's see, when was that? Oh, God, I've already forgot. But anyway, so early chapter 2, you can just take this algebra and do the slightest of little manipulations. Just move the f to the other side, or whichever way you want to think about it. And now, notice that it's written as a level set. Specifically, it's a level set now of this function. Y'all remember that move that we did? Right? If you're given a graph, you can reinterpret it as a level set as long as you're careful with the algebra and make sure you realize you're talking about a level set of a different function. So having done that, forget about all this f stuff. I don't even want to think about this surface anymore as being a graph. I want to think about this as being a level set. And the reason why is this calculus of level sets is perfect. It's exactly what I need. I've got a theorem here that says if you're looking at a level set of a function, all you got to do is take the gradient of that function, and that'll be your perpendicular vector. But yes?
Would you be able to find the cross product of two lines and level sets?
That's a good thought. It will give you a vector that's perpendicular to the surface. But the gradient is not just perpendicular to the surface. It also has a very specific magnitude. So you get something that's parallel to the gradient. Yeah. And by the way, that strategy is another way that you could conceivably, make a solution, that you could find the equation of the tangent plane. It'd be another way to go. I don't think it's quite as efficient as this one, but it would also work. Yeah, absolutely. Yeah. Okay, so all we got to do, once we're looking at a level set of some function, take the gradient, that's my normal vector. So that's the big idea here. It came to us as a graph, But once I've got it re-understood as a level set, then this function g, that function g, take its gradient. The gradient is perpendicular to the surface. Therefore, the gradient is perpendicular to the tangent plane. Therefore, that gradient could be my my little n vector, my normal vector for the tangent plane. So that's the big move. You take this function, write down its gradient, call that your normal vector, and then just, equation of the plane and details for y'all to read here. Make sure you can fill in those blanks. It's, there's the little detail devils that you want to make sure that you're comfortable with. But when you work that all out, what you recover is the equation of the tangent plane. That's exactly what we already knew from way back when. So anyway, I think that's kind of a cool example. This is just numbers. It's explicitly exactly what we just did. Definitely going to let y'all just read this example and give it a look. It's good to see the mechanics in action. Okay. Here's a subtle idea. Subtle but important. Again, we're going to start with a level set. Very important. In this case, a curve, level curve. Some equation, but specifically written as function equals 0. Okay, for this function, can I view y as a function of x? No, not even close. It's crash and burn. Look at this. The vertical line test fails. Right? You can't view y as a function of x. No way. Okay, related question. Harder question. Can I, at a given point, right? Let's say this point. Can I locally view y as a function of x? Now, what do I mean by locally? And this is a subtle new idea. When we say we want to view something locally as a function, what that says is restrict your attention to just that little portion. So we're going to look just at that little portion of the curve. Same equation, but we're only going to look locally nearby within some little what we call neighborhood of the point in question. And locally, that little bit of curve, I couldn't care less about what's up here. That's not local. Right? Locally, this passes the vertical line test just fine. Right? So locally, at this point, yes, y can be viewed locally as a function of x. Right, so that's the question I want to entertain. How can we, in general, given some equation and given some point that I want to look at, how can I decide if it's locally a function of the other variable? Now, sometimes you can, sometimes you can't. Sometimes it's sort of obvious, like here at that point, that's obviously going to be fine. You can draw the picture here and convince yourself that's going to be fine. But at a point like this, it's just not going to work. I claim that's a no. It doesn't matter how small of a neighborhood we draw there. No matter how small my neighborhood is, and now just for effect, I'm going to zoom in if I can. There we go. And that teeny tiny little neighborhood, if I look at just this bit of curve, does that pass the vertical line test? And no, it still doesn't, right? I still have this problem of it hits twice. Does everybody see that? So this idea of viewing functions locally, it gets rid of some problems, but there's some problems that are just, you can't get rid of that. There is something really bad happening at this point. Right? Okay. All right, how are we doing? Is everybody happy? Now let's ask the question, who cares? Right? It's always a good question to keep in mind. Why would I ever care if I can view y locally as a function of x? And the answer is, I might, for example, let's say at a point like that, maybe I would like to look at the the slope of the tangent line. Maybe I want to know the slope of the tangent line at that point. How am I going to find the slope of that tangent line? Well, one thing I could do is I could say, look, locally anyway, this curve gives me y as a function of x. If I ignore all the rest of the curve on that little tiny little green piece of curve, I can say y is a function of x, and then I can say that slope I'm interested in is just dy dx. No problem. Right? Now, in order to do that, though, I do need for y to locally be a function of x. We can only take derivatives of functions. Right? This important fundamental point. You look back to your Calc 1 textbooks, right, from whenever you took that class, and they write down the definition of a derivative. It's always the derivative of a function. You can't take the derivative of anything but functions. You can't take the derivative of a bicycle. That's my joke, right? So, okay, at a point like this, yeah, fine, I can talk about the derivative of that local function, but I can't talk about the derivative at this point, because locally, that's not a function at all. Not even locally. And so the concept of a derivative doesn't even make sense. It's not that I can define the derivative and it happens to be, it happens to crash and burn at that point. No, it's that there is no such concept in the first place. Does everybody see that's a really nasty problem? Is that okay? All right. So, yeah. So if we are going to take derivatives, and if I want that to actually mean something, I gotta know when something is locally a function. All right, now it turns out there's a really nice test. I'm gonna go through the geometric intuition for why that kind of ought to be true. Let's not worry about formalities. The big idea, though, is that if there is a problem, such as at that point right there, a problem, for example, happens when the curve is kind of in the process of wrapping under itself. Right? So the fact that it is at that very moment in the process of wrapping under itself is why I'm destined to fail in a case like this. Right? So it's the wrapping under, which of course means we have a vertical tangent line. And now remembering that this is a level set that we're looking at. Vertical tangent line means horizontal gradient, because gradients are always perpendicular to level sets. Okay. And now let's think about that. What is this gradient vector? Well, this gradient's made up of the partial derivatives of capital F, and if it's horizontal, that means the y partial would be 0. So this is our first little bit of reasoning. First conclusion. Give me a second here. Clean this up. Do this with a different color. If there is a problem, that problem will make this derivative be 0. Like I have written there. And now we're going to write down the contrapositive. This is a important little logical construction. If P implies Q, then not Q implies not P, right? If that partial derivative is not 0, then there's no way you could have a problem. The problem would have caused that to be 0. So not 0 means no problem. So this is our this is our first example of the implicit function theorem. Take the partial of f with respect to y, confirm that it's not 0, and then you're all good. You can view y as being locally a function. Okay. All right, let's see a three-dimensional version of this. It's actually very, very similar. If you have 3 variables in your equation, specifically, I should say, if f is a function of 3 variables, and again, don't forget, we're looking at level sets. That level set is a surface. Something like that. And we can ask these same questions. I can say, okay, let's look at a point like this one right there. If I were to look at a neighborhood, some little small region around that point, and now let's ask, what does that little bit of surface look like? Well, it'd be like something kind of like this. And now just think about this surface that's kind of going like so, right? And you look at that little neighborhood. This little green piece of surface, kind of oriented about like my hand is here, passes the vertical line test. No problem. Don't worry about the stuff down here. It's not local. Right? So a point like this, yeah, everything's fine. You can totally view this locally as being a function. So again, where's the problem going to happen? Well, the problem's going to happen at points like this. And it's hard to visualize, so let me... something like this. There are points, right there, where the surface is actively at that point, at the moment that it is wrapping under itself. And at a point like that, it doesn't matter how small your little neighborhood, it's wrapping under itself, and you're gonna, as I poke through here, right, it's gonna hit the surface twice. Does that make sense? So let's draw this out. The problem happens when the surface is wrapping under itself. It's wrapping under itself when it has a vertical tangent plane. Don't forget these are level sets. And then a vertical tangent plane means a horizontal gradient. Wait a second, what's a gradient? Gradient is all the partials. If it's horizontal, that means the third one is 0. That means the partial of f with respect to z is 0. Is that cool? That recognizable reasoning, right? It's morally equivalent argument. It's geometrically different because, well, it's three-dimensional. Now we're talking about a surface instead of a curve, but it's a lot like the argument we made here. Okay. All right. So there's a pattern that you might have noticed. Let's go up to here. If y is what you want to view locally as being a function, that question is arbitrated by the partial with respect to y. If z is what you would like to view locally as a function, that question is arbitrated by partial with respect to z. It's always the same. That pattern holds. And so, and by the way, here's a really good exercise. If you want to test yourself, do you really have a good understanding of this argument right here? Ask yourself, what would the picture look like and how would the argument be different if you wanted to view y as being a function of x and z? Now it's going to change the picture. It's going to change the fundamental nature of what problems look like, etc. It's going to change which direction the gradient therefore points, and you will come to the conclusion that, again, whatever variable it is you want to view as being a function, that's the variable you take the partial with respect to. So it's a lovely exercise. Give that a try. If you get stuck, not sure where to go, come talk to me in office hours. I'll be very happy to walk you through it, help you draw the pictures, and we'll figure that out. Okay. All right. So punchline theorem. And we've got, you'll notice here, a level set of some function. If one of these variables, one of the variables from that expression, if you want to view one of those variables as being a function, you take the partial with respect to that variable. And non-zero means no problem, just like the other cases we've already seen. So, nice pattern. Always take the partial with respect to whichever variable you want to view as a function. Okay, let's do one. Here we go. So, okay, here is a surface described by an equation. Now, let me recognize I did something convenient here. Be prepared. This won't always be the case. Life comes at you weird sometimes. I wrote this already as a level set. You can't count on that, right? If you've got algebra kind of on both sides of the equals, you got to move what was on the right over to the left or whatever. You move things around in such a way that you have stuff equals constant. Doesn't even matter what that constant is. This 27, I could have put this 27 over here. Totally fine, doesn't matter. All right, so this is the function that I call capital F, because that's the function whose level set gives me my equation. All right, and then with that noted, I asked the question, can I view, by way of this equation, can I view x as being a function of y and z? All right, that's really not obvious. You can't just look at the picture and see it in the picture because I have no idea what that surface looks like, right? So hard question, at least if you come at it from first principles. By the way, let me point out, until you say this expression equals 0, x, y, and z are all independent variables. So how would we even have x be a function of y and z? It doesn't even make sense until you make the observation that I'm looking at what is implied by the fact that I have to stay on this surface, the fact that this expression is equal to 0, the fact that we're constrained to that surface. That's what allows me to think of x as being a function of y and z, just like back here, being stuck on this surface. Let's say over at the point like this, being stuck on this surface is what allowed me to view z as being a function of x and y. The surface itself defines that function. Okay, all right, so how do I decide? Well, per usual, we're going to take the partial of f, that is the function whose level set we're looking at, with respect to x, because x is the variable I want to view as being a function. And it's always the same pattern. Partial of whatever it is, whatever function it is whose level set defines the surface, with respect to whichever variable I want to view as being a function of the others. Is that cool? Everybody understand the pattern there and why I'm looking at this partial? It's all over but the shouting. It's an easy partial. Notice the question is asking about that point 1, 2, 3, so we plug in that point 1, 2, 3. Our answer is non-zero, so no problem, and the answer is, is x locally a function? Why, yes it is. Is that cool? All right, good deal. So let me talk about what's great about this. You write this down, and you got this surface, and if somebody asks you, hey, what's the partial of x with respect to z? A reasonable answer is, I don't know what you're talking about. Am I supposed to infer that x is a function of y and z? How would I know x is a function of y and z? Oh, yeah, wait a second. We've done this calculation. Now I know x is actually a function of y and z. And if x is a function of y and z, I can talk about what would happen if I set y equal to a constant and took a partial with respect to, let's say, z. Now, partial of x with respect to z is a reasonable question. But you've got to establish first that x is actually a function. Okay, so how do I then compute that derivative? Well, there's a couple different ways that you can go about that. I'm going to say this is a kind of a reasonably responsible, sort of full, still leaving formalities out of it. But this is a pretty good take on how to compute that derivative, and as I'm sure you're noticing, it's kind of clunky and scary looking and inconvenient, and good news, we don't really need to mess with this. If you're curious, if you want to see the right and proper take, then come talk to me in office hours, but it's not something we're going to need. Here's a much simpler approach that I think all of the relevant ideas, all the ideas that we're going to care about as mostly engineers, right, are in this picture right here. Let me walk you through the picture. Again, we start off with f being some function of various variables. By setting f equal to a constant, I can talk about that level set, and I want to emphasize by color here, f is now to be understood as a constant. And in so doing, we know how to tell when one of the variables is a function of the others. And I hope you're already uncomfortable. I'm totally breaking one of my own rules, right? If you're going to draw diagrams like this, and if you're going to invoke the chain rule, which I'm about to do, wait a minute, whoa, no. None of these funny business diagrams, right? The diagrams have to be what comes out of the first function has to be the same as what goes into the second function, and everything has, you can't have any of this kind of nonsense that I've got here. So this is a bad diagram. Shame on me. Right? So, okay, yeah, right, absolutely. And if I fixed it, this is what it would look like. And again, I claim this is a much fuss that ultimately boils down to nothing. Right? So let me say we're going to ignore that I'm committing a math crime here. This is a math crime that will get us to the right answer reliably. And this is going to be good enough for our purposes. And so this is okay for us to do in this case. Okay, so now we've got x is a function of all these other variables, and let's ask the reasonable question, how do I take its partial with respect to xj? Well, partial means all the other variables are to be held constant. Whoops. X. Right, so here's our diagram at this point. F was a function of all these other variables, but I've set it equal to a constant. And now I've got this implicit function xi as a function of all these others, and I'm taking the partial with respect to xj. So there's a lot going on. It's a lot to keep track of, but that's a variable, that's a function, that's a constant at this point. Is that cool? Is everybody with me? All right, and now I'm about to use the chain rule. I'm going to apply the chain rule and see how do changes in xj contribute to changes in f. And I'm going to answer this question two different ways. When you change xj, how much does f change? And the first answer is the easy one. The first answer, how much does this thing that's a constant, how much does it change? Well, it doesn't change, it's a constant. So, right off the bat, the answer's got to be 0. Well, the answer is 0. F's not allowed to change. Okay, here's the second answer. The second answer is, well, look, changes in xj can propagate along that path, which gives that term, and they can propagate along that path, which gives that term. So the sum of those two terms, that's also how much f changes. So that means that we have this equation here, right? And, oh, wait, what we were interested in, we were interested in this. We're interested in the partial of xi with respect to xj. Okay, cool. Solve for it. And there's your formula right there. Is that cool? Is everybody happy with that? Okay, there's a few things to say about this. First, let's talk about this minus sign. That minus sign's a big deal. A lot of people forget the minus sign, but much worse, a lot of people don't believe the minus sign should be there. A lot of people think that minus sign is a mistake. It's not. That minus sign is absolutely correct. It's absolutely supposed to be there. But here comes the tempting, very tempting, but ultimately nonsensical reasoning. And that is, you can probably even see this coming. Hey, wait a minute, don't these cancel? Partial f and partial f, those are the same thing, aren't they? We just cancel them right off of there. And wait a minute, isn't the denominator of my denominator a numerator? And isn't the the denominator of my numerator, isn't that a denominator? And isn't this just right without the minus sign? It seems like the minus sign shouldn't be there. You see the tempting, right? Very, very, very alluring. And you're gonna, there is this pull to think, hey, yeah, maybe there's no minus sign there. Well, this is nonsense. Because, because, as I'm sure you've noticed already, these things are not the same. That's notation. That's notational nonsense. These things that we write as fractions, they're not fractions in a broad sense of these being independently well-defined objects. They're just not, right? So from the very beginning, from the get-go, when I said I was going to cancel that with that, that's nonsense. And we've seen this kind of nonsense previously, right? Hope y'all remember. So that's nonsense. Okay, so all right, so that reasoning doesn't work, but still, I kind of feel like this is counterintuitive. So let me try to give you some satisfaction of why that minus sign actually makes sense. And here's my argument. That minus sign, I mean, if you think about how the algebra works, we solved for this to get that, and of course you have to move something to the other side of the equation to get it. That minus sign effectively comes from this plus sign. So I'm going to rephrase the question as, why do we have a plus sign here? And I think there's a pretty good answer to that question. Why there's a plus sign? Because we're talking about two separate contributions. That path contributes that term, and this path contributes that term. And the whole point to looking at these two separate contributions is they have to add up to 0 because f's not allowed to change. Right? F can't change. So these contributions have to be opposites so that they can add up to 0. And thus the plus, and thus this minus. I mean, again, that's, for whatever little satisfaction that might give you. But that's satisfying to me. I hope that might be satisfying to you. Any questions about that? All right. Okay, so now real quick from a testing standpoint, very important to remember that minus sign. A lot of students run with the mistaken impression that sign errors are no big deal. It happens to the best of us. So let me make some distinctions here. Absolutely, there are certainly some kinds of sign errors that happen to everybody, and we're only human, right? Look, sometimes I count, like I was passing out test papers on Friday. Sometimes I miscount. I know how to count, but I get it wrong sometimes, right? And if I get it wrong, it doesn't mean I don't know how to count, right? So the silly trivialities, of course, happens to the best of us. So, importantly, not all sign errors are of that sort, right? This minus sign is not a whoopsie doodle, I can't count, right? This this minus sign, and therefore if you leave it off, the resulting error, it's a big deal. This minus sign is what distinguishes your work from the work of someone who thinks that it shouldn't be there because these cancel. Right? And you got to keep in mind when we're grading papers, right? We're looking for evidence that you understand, that you have the right point of view and that you understand the ideas that are going on here. If you write this down with no minus sign, it makes it look like you think that cancellation works, and it's just fundamentally wrong. Does everybody see why that's it's a bad look, right? So, look, the reality is then when you're working at a problem like this, getting that minus sign right by itself, just the minus sign, probably worth several points. Now, you can view the glass as half full or half empty, right? The half empty take is, oh my gosh, what a harsh penalty for a minus sign. The glass is half full take is, oh my gosh, I get like several points just for writing down a minus sign. That's the point of view that I encourage, right? You get that minus sign correct, that's worth money. Okay, so please go to the trouble and make sure you get that minus sign right. Let's do one. Here we go. You'll recognize that we've got here the same surface we've previously looked at, where we have already established that x is locally a function of y and z, right? We already did that work. We know x is a function of y and z. And because x is a function of y and z, I can reasonably ask about its derivatives. That's definitely not a bicycle. It's definitely a function. And if you've got a function, you can talk about derivatives. Here, we're taking the partial with respect to z, for which purpose y will be a constant. Is that cool? Is everybody with me? Okay, now here's the problem. This example that we're looking at has variables called x, y, and z, and that's not how this was set up. And by the way, it won't always be like this, and it won't always be like this, right? Maybe the variables might be p, q, l, and i. Something like that, right? So try not to memorize formulas in terms of the letters of the alphabet that get used specifically. So I'm going to show you how I remember this formula. I think this is a good take, and it's a little uncomfortable in a way, but I think it's very practical. When I want to write down an implicit partial derivative, very first thing, get that minus sign on the page. Get that done first. Don't forget that minus sign. It's such a big deal, right? So again, easy points. Free points. Get your free points. Okay? And then, having gotten those free points, then, nonsensical though it is, play the game where you're like, oh yeah, and then it's kind of like as if those cancel and as if this came from there and this came from there, right? So that that's not true. It's false reasoning, but it's a handy little memory tool, right? So minus sign first, and then write down the partials of f exactly as they would have to be to make the fake, nonsense, bogus cancellation seem to work out. Everybody see what I'm endorsing there? Okay. All right. So, and then it's all over but the shouting at this point. Couple of partials. These are easy partials to compute. Again, we're interested in this point right there, so don't forget to plug in that point. Arithmetic, victory. All right, okay, last little thing I want to talk about on this, and then we'll move on to the next thing. This example is actually kind of two examples that combined are really a full example. So the very first thing we did is we asked, is x locally a function of y and z? And we, have a take on how to answer that question. Second, after having established that x is a function of y and z, we then, remembering that we already established that that's a function of y and z, then we compute the partial derivative, with that formula, et cetera, et cetera. In practice, day in and day out, it will not be broken down like this. Okay? In practice, you're going to see questions that look more like this. You're going to have some surface. By the way, this applies on exams, and this also applies on just in real life. Like, when you're in some future engineering class, you're going to have some equation that describes the whatever situation you're looking at from engineering, I don't know, whatever that might be, you have some equation and you're going to be interested in, hey, wait a second, when I change one of the variables in that equation, how does that affect this other variable? You're going to want to write down a partial derivative. And so it will just naturally come upon you as, here's an equation, how do I compute that partial derivative? And you, as the user, right, you as the practitioner of the method, have to be responsible to remember, step one is to try to establish, how do you know that this is even a function in the first place? That's part of the user's job. That's your job as the practitioner. You've got to establish first that it's a function. And only once you've established that it's a function is it even reasonable to ask the question, well, okay, then what's its derivative? Right? So you will first do this work, right? And then you will second, having done that, you will do this work. And by the way, just from a strategic standpoint, I know y'all are about in a month, y'all will be taking a test that will cover, among other things, stuff like this. On a test, these will be about equal in grading. So if there were a 10-point question that says, here's an equation, compute that partial derivative, probably about 5 points will go just to your work establishing that x is actually a function. And then the second 5 points will come from doing the computation. Yes?
X is no function until I stop the question.
I wouldn't do that. Oh gosh, what would I do? Oh, I would have to phrase the question in such a way as to admit that possibility. Off the top of my head, I'm not sure exactly how I would, because I wouldn't want to phrase it in such a way as to give away the game, But yeah, if you are unable to confirm that it actually is a function, then you don't want to proceed to taking derivatives of it. Yeah, absolutely. Yeah. And again, as a test writer, I would be very mindful of awkward. I don't want to put y'all into a situation where I've asked you an impossible question, right? So one thing I've done in the past is I've got this you probably noticed in my old exams. I've started talking about this guy named Bob, right, who gets stuff wrong all the time, right? And I would be like, okay, your friend Bob comes to you and he wants to take the following partial, and he says that he can blah blah blah. Help Bob understand the situation. And then, as you say, the punchline might actually be, yeah, he can't take this derivative at all. Yeah. Okay, all right, so do be careful. Again, these are about equally important, and certainly checking that the relevant variable is locally a function. That's probably about half the point. So again, heads up. Okay. All right, let's see. We've got a couple minutes left. I'm going to do a couple of quick things at the start of 3.2 here. But this first part of the screen here is arguably the most important stuff for this section to the course. The rest of 3.2 is kind of certain computations, and I'll say a couple things, but we're going to be quick about that probably later. What I want to talk about here real quick is this idea of a parametric curve. You all know what a parametric curve is. And just a few observations. We know that there's the velocity, that's the derivative. You can write down the velocity vector. It'd be something like that, maybe. I don't know. Some vector. I hope it doesn't seem unreasonable if I write down dr equals r prime dt. Let's think about what that would mean, though. What is this dr? I mean, from the notational standpoint, dr dt, and slide the dt over. Hopefully this is probably familiar. But what do I mean by dr? And I want you to keep in mind, d means differential. Differential means a linear estimate of change. So dr, r representing position, this says, what is our linear estimate of how much position changes along this curve. And the linear estimate of change in position would be something like this. It would say, well, look, I figure we're probably going to be going about with that same velocity. So I figure we'll probably end up about here. R prime times dt, whatever that is. Now, the reality won't be that. The reality will be that if you started here, you would actually end over here on the curve. And the curve, of course, it might bend or who knows what. We're just doing a linear estimate. We're not going to get the exact right answer. But dr is our linear estimate. It's what I like to call the position differential. I was here. This tells me how much I expect my location to change based on what's going on at that point. Okay. And then let's see here. Oh gosh, am I out of time? I think I'm out of time. We'll pick up here. We'll pick up here on Wednesday. So y'all have a good rest of your day. See you later. Yeah.